So in this video, I'm gonna go over these contents. First, I'm gonna go through a realistic fluid dynamic case. As uh, as I go along, I'm gonna explain the what is meant by a state and also what is meant by a control system, a control input, and eventually at the end, I'm gonna explain the physical meaning of the solution of a linear time variant system. So let's jump in with the first two content. I'm going to first show a realistic fluid dynamic case or a situation, and then as I explain or show you the situation, I'm also going to define a state and as well as the control input. So this is a work from 2017 that I did during my bachelor's. The paper is here, the numerical simulation of fire in a multi-stored ready-made garment factory. So here you can see a 7-story building basically. So here like the whole research was what happens if there is a fire incident in somewhere in the building. So we can see the sketch or the layout of the building. There are multiple rooms and like what happens if there is any fire in somewhere in one of the room. The fire and smoke propagates to different rooms and to different floors, and the whole work was to study the dynamics of the flow of fire and smoke. So here this shows the simulation of the smoke propagation through different floors and different rooms. We can see like over the time. So if this is t is equal to 0, this is going to be the next time after the next time step, and this is after the next time step, and this is the final simulation scenario. So each of these are basically capturing the situation of the dynamic event that is taking place after a fire incident has occurred in the building. So all of these different pictures are basically called the states of the system. If we define the whole thing like there is a building, and in the building there are fire incidents, and a new physical fluid dynamic phenomena is about to occur, and this is going to occur, and like we're going to see the change over time, and that whole thing we define as a system. So the system if we take captures of the system at different time, that is something we call the state. So here we know that we know the system, and when we capture it, so this is one state, this is the next step, next state, and this is the next state, and this is the next state. So basically from here, from this point to the final point, there is not just 4 different states. There are actually infinite states, but we are taking 4 states to show the different points from initial state to the final state, and these are basically showing the significant changes so that we can plot a curve. So this is what is meant by state, and that we talked about. And then the next thing that I wanted to also define is what is meant by a control input. So control input is something that basically we provide an input to control a system, but here we're not controlling anything actually, because this is a natural phenomena that somehow there was a fire and that the smoke started propagating to different places. We are not controlling anything, but at the same time, the concept of input still works here because it works in the same dynamic equation. So here the input is gonna be the fire itself. Like the thing is that, so just think like if there were no fire, there would be no smoke. And from this time to this time, if we take different captures, we will see no change. But all of this change from here to the final state has been driven by the fire. So the fire has been constantly fueling the event or acting as the input. So here the fire or the smoke, whatever, this thing we will define as the control input. Not the control here because we're not controlling anything, but basically we would define it as an input. Okay, so now as we have a like rough understanding of what is a system input and what is meant by the system state, we move to the next part. So if I go here back in here, and we will see that the system characteristics, the system, when we're saying that this is a system state, like we can see like many of the black portions like inside each of these pictures. But what are those basically mean? Those are smoke. So smoke is like if we like in plain words, smoke is like basically a flow of some like fluid. But the thing is that it can be associated with a number of different characteristics. For example, this smoke can be characterized by the temperature. Also, it can be characterized by visibility and many other such properties. So we can actually redefine our state as a combination of many other individual states. So all the temperature, as we talk, temperature and visibility, those are also like those are something that we can also use to define our whole system, right? And so the temperature we can define as one particular kind of property, and the change of the temperature will also be a state. Similarly, the change of the visibility is also defining the whole system, like how the system is behaving. And that's why the visibility itself can also define another state. So we already see that here we instantly come up with two different states that are useful to define the system. So here in this figure, we can see that this is showing the change of temperature over time. So this is basically, so this one, the figure 7.A is one single state, but B is showing how this state is changing over time. We can see that the temperature is not that much, and at one point it just shoots up right along the vertical direction. So this is definitely not linear. It seems linear until a certain point, and then it becomes like it doesn't behave that way. So this is the change of state over time. So the change of state is the differentiation of the state basically, which is gonna be if I consider is x of t or x1. State is normally defined as x, so the change of state is going to be x dot t. So similarly, this is another property which is visibility. This is also a screen capture of just one state, but when we want to see the change of state, we go to the B diagram where this is basically showing how the visibility is changing over time, and this is not linear phenomena. So right now, it should be clear what is meant by a state and how we define state in a like practical physical problem. Basically, it's how we see the physical thing. We define each of the characteristics or each of the property as a single state and want to see how that state changes or changing over time. And when we combine all of this property, it's creating a little bit more complex problem. But the thing is that if we can accumulate or if we can combine all of this state together, this will define our final capture or picture of our dynamic system. And why we are actually decomposing our state into smaller or like independent states, because it makes the simple problem simpler. And when we combine that, or like when we see that as a state, this as a state, the whole problem becomes way simpler and more computable. Now, next we are gonna move to the last section, which is physical interpretation of the solution of a linear time variant system. So here, whatever I explained in this slide, like the whole thing, and I said like there are two states that I defined here, like for this presentation, and the second one was visibility. So I'm gonna describe the physical meaning of the solution of the physical meaning of the state of the linear time variant system, just for this one, to make the whole situation a little bit simpler to understand. So I actually I have redrawn the building like in a very simple shape. Said the whole building is just a single room, and it has just one window, and we are only definitely there is a fire incident somewhere inside the inside that room. This is the one room building, and there is some fire incident, and if there is a fire there will be smoke, and it will basically try to accumulate, and also it will get out of the window. This is the window as well. And so we can kind of capture this, like how, say, we have a camera here somewhere that captures the frame enclosed by this window. And so whatever we can see of through this window is basically the state change of the visibility. So here, for example, at the very beginning, when there was just starting of the fire just started, there was almost no smoke. And see, there like it's completely white because there is no smoke yet. So, and the time is T0. And then as the time moves forward at T1, the input is fueling the input. What is the input? The input is fire. So it's inputting, it's providing the smoke, and this is making the skin bigger, like blacker. So more black means there is more concentration of smoke and less visibility, basically. So that is kind of the next step. And then as time goes by, we can see that it becomes darker because there is more smoke concentration. And this is like the final step where it's like totally black. But just to explain that again, so the whole thing is there was what happened. There was multiple thing happening when the fire incident actually occurred. There was temperature change, visibility change, and change of many other properties like in the room ambient. But we only considered the visibility to just narrow down the problem. So even if we narrow down the problem to just study one single state, that is the visibility, still we can see the visibility change over time. So this is like an actual simulation that I did over the period of time. Say that was in seconds. So it's 1/62 or like more than 2 minutes. And we can see that the temperature, the visibility change was like this. And as I explained, this is definitely not a linear problem. This is a non-linear problem. And the whole visibility change phenomenon is non-linear fluid dynamic problem. But we can always approximate a non-linear problem to a linear problem, like at a small interval. So let's assume that this problem, or let's consider that we have linearized this non-linear problem to a linear time variant system. So right now, even though it shows a non-linear curve, we're assuming that this is linear. How? that is a different discussion. I'm not going to go there, but I'm just going to explain from here what is actually the meaning of the linear time variance system, or like how the state actually changes over time for linear time variance system. We have seen the simulation, how it changes here, but mathematically what is actually happening there. But now first let's see what is the equation for the linear time variance system. So this is the equation for the linear time variance system. So x dot, as I said, this is the change of the visibility, the change of the state. So this change of the state is something that will always exist if the system is dynamic. So our system was dynamic from t0 to t0 to tf. As the time was proceeding along the time, the dynamics of the environment in terms of just the visibility, definitely as we narrowed down the problem only in terms of visibility, had been changing, and that was driven by the fire. So as there was a dynamic change in the visibility, there was also change in the state, and that change in the state is defined by this equation. And here we can see there is a xt b ut. U is our input that I defined, basically the smoke or the fire that was driven the whole dynamics. And also there is state. So state itself, and the A and B are two different matrices. So A is called the system matrix. So, and B is called the input matrix. So B is associated with the input and A is associated with state. In other words, B defines how our system will perceive the input, and A defines how our system would react with the initial state. Remember, the thing is that when the system changes, the change of the system, how the system would look in the next moment, also depends how the system was in the previous moment. Even though, just think, there was T naught, and then there was T1, T2, and there was like smoke there, some sort of smoke, and at the middle of the event, say someone stopped the fire and there was no input because there was no smoke, no incoming smoke, but there was existing smoke in the room, already some existing smoke. So that is not gonna let the event end at the same time when the fire was stopped. So even though the fireworks was stopped, say at t is equal to t3, the phenomena will still be dynamic after a while, till after a while, say after tf, until tf. Though it will not, like the change we will not see in the same way that we are seeing right now when the fire is always acting from t0 to tf, but there will be something happening, and that would be driven by just this portion. And until when the u was 0, so this is called the zero input state response. Anyway, I'm not going to explain that either. I'm just going to show the solution. So the solution is more interesting. So here, like if we solve this problem, if we solve this single order degree differential equation, we're gonna find the solution as xt is equal to phi of t naught x naught plus integral of phi of t tau b tau u tau d tau. Now this definitely comes after just integrating this one and defining a new term which is called phi t naught. So even though this equation looks very complex, I wanted to explain how does this physically explain our scenario, or like for any scenario, what is the physical meaning of this solution of this equation. So because this is just like, even though this is just a math, every math has its physical meaning. So that's why I wanted to make this whole video just to explain this single equation. So let's see this. So this equation, we have two different portions. The first portion is this, which has, which is called free or natural response. Just think. So if I didn't have this portion, this second term, then this portion, this the first portion corresponds to ATXT, as we said, like when there would be no input, say u is equal to 0. If there was no input, then this whole term would drop and we will just have x dot is equal to at, and the solution would be xt is equal to phi tt naught and x naught. I'm going to explain what is phi tt naught later, but just want to tell you that what happens if the control, if the input is 0. The input is 0 is going to be this, and this is called zero input response of the system. It basically physically means that the fire, whenever we're talking about there was fire was stopped, and then we started measuring. When the fire was stopped, there was no input, and the system or whatever dynamics we were seeing, that was the free or natural response of the system itself. The system, there is no input in the system. It was like already how the system was supposed to behave under the fluid dynamics law. It would behave that way. But whenever we start inputting this response, the input driven response, or the input itself, it's gonna interfere with the natural response, like that is calculated in terms of fluid dynamics, like natural fluid dynamic equations. It's gonna interfere with that, and like add another effect on the x. So the visibility decrease will be also like increase with this term when we have an input. Again, if there was no input or no fire, there will be less visibility issues, right? It would be only driven by the available smoke. But when there was an input, it will be actually worse, because the effect of the input will also be there, and this summation of these two terms will be worse than just this single term. I hope this is clear. And then next, we explain term by term. What does each term mean? So for that, we'll need to know what does this first matrix means, phi of t naught. So phi of t naught, this is called a state transition matrix. So state transition matrix works like magic for any linear system, be it time variant system, time invariant system. How? So physically, this thing, this is basically a matrix, but this one works like a time machine. So time machine, what does a time machine do? Time machine takes you from a time to another time. The same you, but it will take you from one time to another one. So just think, this is a machine, but this is a time machine. So this time machine, just right now, let's start explaining our equation. The first time, the free response. So this one, the phi of t naught is our time machine, and in the time machine, what we are inputting? We're inputting this x naught. So what phi of t naught is doing? Phi of t naught is taking x naught to a different time. So x naught is what? X naught is the visibility condition at t is equal to 0, like the initial visibility condition, right? Which we can see this one. This was basically, there was no smoke. It was like this, or, ideally, this is not the case, as there can be some initial condition. For example, we can start with a situation where there was almost already some smoke. So if there were almost some smoke, then over time that smoke will start decreasing, because from the room the smoke will go out and there will be less smoke, and at one point it will clear out. But that is what this thing is doing. This guy is having this input t and t naught. So it's basically taking whatever is on the right here, t naught, from time t naught to time t. T is the final time. So the whole thing, if I go back and start explaining physically, this one is our initial time. Just consider this one is 0. So there was no input, and we start with a situation. We start with a situation where there was initially some smoke. So the smoke will track the whole dynamics, and the smoke itself is a state. So the smoke driven visibility, itself is the state in our consideration. So that is x naught. But the thing is that x naught will change over time. And we are more interested to know what is the condition of the state after time t. So at time t. So at t naught it was x naught, but when we multiply this thus with the state transition matrix, the whole thing gives us another matrix xt. So this we disregard this portion. So this one would be equal to this one. That means x naught will be taken to a different state xt, which is the final state. And this is our time machine. So that is called the free natural response. Now, the next part is this. We actually didn't have, say, the input is equal to 0. So if that is the case, then this relatively more complex term comes into account, and then we have to define it from the right to left. Just think, what is d tau? D tau. Tau is a different parameter that is basically defining time as well, but we're writing it because we want to measure it in terms of our time in consideration. And dt is an infinitesimal time, a very small time. Sorry, d tau is a very small time, and within this time some phenomenon is occurring. So what is this phenomenon? At infinitesimally small time, which is a small change of time, say from t naught to the very next moment we are going, that is dt, and there will be, within that time, there will be an input. That means there will be a smoke induced by the fire, and that is ut. So this u tau. So the u tau corresponds to the input at that very small time, and this is provided by the fire, or it can be by us. Like for different system, this is the user input. But what is bt? B tau. So as I said, this B is another matrix which is called the input matrix. So B basically means how the system perceives our input. So different system perceives the input differently. You can put the input, just think like in this room, say initially there was temperature 25 degrees Celsius, and like we had certain humidity because we were in, say, one country, and then we can consider another country, or say a country which has a cold environment, and then the ambient will be very different. So even though the fire is the same fire in country 1 and country 2, the ambient will react very differently because this is not the same. So how the system would react to an input is basically defined by this matrix, input matrix B. So it's a system characteristics. So if we study a system, we'll know that, okay, so this is how whatever input you provide, it will behave a certain way, and it is determined how is the physical condition of that system. And so again, we go from left to right. So from right to left, at a very small time, there is an input that is provided into the system, and that goes through b tau. And so this three multiplication of this theta term means at time tau, how the input contributes to the state. So it's basically this three term is actually a state, and that adds up to this one to make this. But the thing is that this has to be in the same time as this one and this one, but this is not in the same time. This is in a different time. We're assuming this is at how. So we have to change it. We have to know how the system perceives or how the dynamics changes this contribution at our desired time, which is t. So it goes to the time machine or the state transition matrix, and after multiplying with the state transition matrix, we get the effect or the state at time t instead of tau. And whatever we're talking the whole thing. This thing is actually for infinitesimal time, so very small time or very small effect. So every small input effect is providing a state contribution to the state. And so the question is, so there are a number of such dt which we need to integrate, or this number of such that corresponds to number of such contribution to states that we need to integrate over time. And when you integrate it from t naught to t, we get the summation of all those contributions over all the time. So that's how this whole thing means, basically overall contribution of the input driven response. And that's why we're integrating, and that's how we have each of this term written and in this certain order. And so finally our state means the summation of both the free response and the input driven response. So this is quite amazing. I just wanted to explain the physical meaning of this, because this is pretty cool, and this is also applicable to my research work that I did almost 10 years ago. But this is quite interesting how we do that, and after that we can actually start controlling the system. So thank you very much for attending the lecture. Hope you enjoyed it, and see you in the next one.